Welcome back to ECE 442-542. This is now working through some problems based on the first exam and the unit quizzes since the first exam. And I'm going to do this rather quickly. I may just sketch some of the solutions. You should know the answers. You can find those answers from the material either here or in your quiz sections or the solutions to exam number 1. And I'm being a little bit selective with the problems that I'm working, and these problems are really the ones that were the most challenging by the majority of the class throughout the semester. The first one we'll talk about is time constants. I really think this was a challenging problem just because you weren't maybe completely thinking through what's slow and fast, or you just quickly did something in a hurry and didn't think about long and short, etc. But here, let's say we have an analog system. You might need to sample that system, so in that case you're focusing on the fast mode, but you can identify the modes in this analog system. You look at the poles, and those now produce modes at e to the minus 1/2 t. Your poles are at minus 1/2, minus 4, and minus 10, the values of s that cause the denominator to vanish or to become equal to 0. We have a slow mode, e to the minus 1/2 t. That decays much more slowly than this fast mode, e to the minus 10 t, and we actually have a mode between those at e to the minus 4 t. You can now use those modes by looking at the exponent, and you can say, oh, I need that exponent, forget the sign, I need that 1/2 t, I want the time t when that equals 1. So now I set 1/2 tau equal to 1, and my time constant now is, solving for tau, 2. Doing the same thing for the other two modes, we have a time constant of 1/4 and 1/10. You can see that the short time constant corresponds to the fast mode. The long time constant takes now much longer for that to decay, and if it's a 1% decay, usually you think of 5 time constants. So this particular response, without any control, if you just had some initial conditions, this would then basically, those initial conditions would be gone effectively after 5 time constants, or 2 times 5, or 10 seconds if our time axis is in seconds. Z-transforms and region of convergence. We need to be comfortable with this. Here I've actually illustrated 3 different functions, x sub 1, x sub 2, x sub 3. They have the same exponential decay of 1/2, but they now have different start times for when they become active. The first one starts at time 0, n greater than or equal to 0, and goes on for non-negative values of n. That's a causal sequence. We could find the region of convergence by looking at when this particular waveform or function converges in the z-transform, and we would find then that we would need the magnitude of z to be beyond 1/2, and because n does not possess or go in the negative time range, or you don't have a negative index, this region of convergence goes unbounded. It goes off to infinity, so I'm not putting anything here to bound it on the upper side. The second waveform starts at time n bigger than 3. That's causal as well. Both of these on the top are right-sided. A causal sequence is always right-sided. You can't go the other way. A right-sided sequence is not always causal. But here, if you looked at the common ratio between terms in finding the z-transform, you will see that this region of convergence is exactly the same. Even though we've started later in the time index, our common ratio is the same, and so our region of convergence, again, the values of z that cause that z-transform expression to have a bounded result are those values of z that live beyond 1/2 in the complex z-plane, and it's not restricted to being less than infinity. That's not the case for little x sub 3 of n, because now we are going a little bit, we're going a finite distance into the negative time axis. We now have some negative time indices. This is no longer causal because it's starting before time n equal to 0, but it is right-sided. If you look at what we need for region of convergence, we will see that we need z to be bigger than 1/2, but because we have this sequence defined for a finite number of negative indices, we can't let the region of convergence go unbounded. We have to bound, so we have to keep that extreme value of in our region of convergence away from the region of convergence. Infinity cannot belong. So you'll need to be able to do this for the anti-causal or non-causal, and then the corresponding left-sided sequences, where those then cannot possess the region of convergence, cannot possess the extreme value of z equal to 0. If you now look at finding the z transforms of these, you could, by the definition, this is the sum from -infinity to infinity. Little x sub 1 is only defined for n positive or non-negative. You can then go through the algebra. You can look it up in a z transform table and find that the z transform is z over z minus 1/2 in terms of powers of z. If you want to write this in terms of z to the -1 powers, it's the other expression. X sub 2 of z, now we are actually beginning the summation later in time, so we're summing from 3 up to infinity. You could do exactly the same analysis that we've done. We've already found, or you could say, wait a minute, we just found that z transform that started at 0. I just need to remove some of these values in that sum because I was starting at 3, and because of that I can take those away. You do the algebra either way and you should end up with now this expression for x sub 2 of z. I will let you figure out how to treat the z transform. Now we would be starting for x sub 3. We would have to begin below 0 in terms of time, but you will have something that looks similar. Look at this. This now still has this z to the -1/2. This has a z to the -1/2. So you would expect that factor to be present here because we had delayed in x sub 2 the start by a few indices. That's now giving rise to this additional delay term, or this delay term there, depending on how you write it. You can write it upstairs or downstairs. That's why that now appears in that expression. Moving on, let's now talk about block diagrams and how do we go back and forth, how do we dance in this 4-squared representation of these different ways of describing systems. We can now say, oh, here's our output y of n, there's our input u of n. If somebody now wanted a state space representation, you would immediately say, oh, what I need to do is define my state variables as outputs of these delay blocks, and then I'm good to go. I can now say, oh, what precedes that delay, if the output of that delay is x1 at time n, and that's a delayed version of what came in that box or that delay block, then what came in on the input side must have been one time period before. Likewise here is x sub 2 of n plus 1. Now from that you can actually write down your state space representation. by looking at what is producing, and you now need to make sure that the right-hand side only contains your state variables at the present index time, little n, and the input is at the present time, u of n. To find x1 of n plus 1, that's the output of this summing junction. We can now find what are the signals going in. We have 4 u of n. We have x sub 2 of n, and we have 1/8 from x sub 1 of n. Likewise, for x sub 2 of n plus 1, we have 2 u's. We have 1/2 from x sub 2 of n, and we have 1/4 from x sub 1 of n. And if somebody now said, oh, well, you need to know the output equation as well, in this case, there's no direct feed through from here out to the input. That's not there. That then says that one's 0. Y of n is only made up of a linear combination of x1, and it's just x1. So there is then our state space representation, and you should be able to then go back and forth. You could now z-transform that state space and find a transfer function. You could do the block diagram algebra and find the transfer function between u of z and y of z, etc. You could now apply a step input to this system and find the structure of your output. You can now just do all sorts of things with this system representation. Suppose somebody now gives you a transform expression, capital X of z, and they say, oh, here's your region of convergence, and I now want you to find what is the time sequence. Now is when you need to remember what's happening. This particular region of convergence, z values are now less than the smallest pole. You'd first want to factor this, and I'm now not trusting my factoring capability after the most recent video series, but now we have this factored, and we have a pole at 2 and a pole at 3. This now says, oh, our region of convergence is interior to all of our poles. That now says that this is corresponding to an anti-causal system. We can now find, using partial fraction expansion, we can now find how these modes are weighted in the time domain by doing this partial fraction expansion. Maybe I'll just go ahead and write that in factored form, so that now we have an a1 over a z minus 2 and a b1 over a z minus 3. You should be able to now do the cover-up method and find a1. a1, if you do that, will end up being 2. b1, you do the cover-up method, replace z everywhere with 3, and now you see that you have 9 minus 8 upstairs, or 1, divided by 3 minus 2, or 1 downstairs. B sub 1 becomes 1. X sub 2 of z, if we now multiply both sides through by z, we have 2z over z minus 2 plus z over z minus 3. Now, because it's non-causal, because we have this, now you need to make sure that you're staying focused because of this non-causal, or in general, more generally, if you had a left-sided sequence, you now need to make sure that if you're dealing with a z-transform table that's a standard table, and most of your standard tables only deal with causal connections between the time domain and the frequency domain, you need to invert the sign that's between those time domain and frequency domain pairs. So invert the sign between x of n and x of z, and what I'm going to say is a standard z-transform table, where this standard that I'm suggesting is now, because typically your tables only possess causal entries, but some tables might do otherwise. But now that we know that, because if we had a causal relationship here, we would just say 2 times 2 to the n plus 1 times 3 to the n for n greater than or equal to 0. But we don't have a causal, we have a non-causal. That means we have to invert the sign between the z-transform expression and the time sequence expression, and this is non-causal, so this is now for n less than or equal to 0. And that's now what we would produce or create from that z-transform question. Determine the exact system matrix phi. This is now phi, and it's wanting the exact, so that now says that we need e to the at associated with a zero order. That probably shouldn't be there, but a zero order hold equivalent. So we're looking to find capital phi, which is e to the capital A t. And in this case, you maybe weren't given capital T, so you have to put that into or leave that variable in your expression. Now we want to know, well, what's A? Well, we can find A. That's from this continuous time system. A is now minus 3. That's an input, so that's not in our A matrix. We have a 1 there and we have a minus 2 there. Hey, this is lower triangular. That's not going to be too challenging to invert or to work through. But now we know that phi is e to the at, which is in fact the inverse Laplace transform of si minus a inverse with little t replaced with capital T. In this case, this matrix si minus a, and I'll invert that in a minute, but now we have s plus 3, we have minus 1, we have nothing, and s plus 2, and we want to invert that. Well, the inverse of a 2 by 2 is fairly straightforward. We simply take the determinant, which in this case is the product of the diagonals minus the product of the off diagonals. We have a 0 in one of the off diagonal terms, so we just have the product of the diagonals. We now interchange the diagonal entries and we change the sign of our off diagonal entries. And that's now the inverse of that matrix. We need to inverse Laplace transform that. Well, let's now distribute that denominator into all four terms, and we have 1 over s plus 3, we have 1 over s plus 2, s plus 3, we have nothing there, and we have 1 over s plus 2 there. Now we simply need to do 4 inverse Laplace transforms. That first one is e to the minus 3t. The next one we can do the partial fraction expansion. That's now this. Again, we can do the cover up and find A1 and B1, and if you do that, hopefully, well, here I've interchanged what I was going to do, but let's do the A1. We cover up the s plus 2, we replace s with what's left with minus 2, and we end up with A1 being minus 1. Is that true? No. So now A1, we cover up the s plus 2. Maybe I should have used the same partial fraction expansion that I did in my notes originally, so let me do that. Then maybe I won't get so messed up. Let's call that A1 and let's call this B1. A1 now is going to be, we cover up the s plus 3 on the left and we replace s in what's remaining with minus 3, and A1 now becomes minus 1. B1, we cover up the s plus 2 factor on the left in the denominator and replace s with minus 2 in what's remaining, and we're left with 1. So that now in the lower left hand corner we have 1 over s plus 2, which just ends up being e to the minus 2t, minus 1 over s plus 3 inverse Laplace transformed, which is e to the minus 3t. And in this 2 entry, that's now e to the a little t. To find e to the a big T, we simply replace little t with capital T, and we're done. Next problem. Now we're into Ragazzini control design. Suppose we're given a plant, g of z, and one wants to control this plant using the Ragazzini controller design approach. Suppose the desired closed-loop transfer function t sub c is to be designed to yield a settling time close to 20 samples. Which closed-loop transfer function would be valid? And here you're shown what the answer is. So how did we end up with that? Very first, if we're doing this, we now say, oh, we need our denominator poles to be dominated by, or to have an R value such that we have a settling time close to 20 samples. That says that n sub s is equal to 20. If we go back here to our summary page, we say, oh, we can now use this expression, 1a, r is equal to 10 raised to the minus 2 over n sub s, so that now r is equal to 10 raised to the minus 2 over 20, and that ends up being approximately 0.79. And good, that's making us feel warm and fuzzy because all of these denominators have a z minus 0.79 factor. We now know that t sub c of z is something with a z minus 0.79, so that was kind of given to us, this part. Do we have any? Well, restriction 1 says, what's our pole zero excess? We have 2 poles and 1 finite zero. Our pole zero excess is 1, so we need t sub c of z to have a pole zero excess of 1. If we don't have anything else, that would be a pole zero excess of 1 in t sub c of z. Restriction 2, we do not have any unstable zero factors, so restriction 2 we don't need to worry about. Restriction 1 we have right now being satisfied. Whoa, restriction 3 is in play. We have an unstable pole at 1.5. So restriction 3 now says that we need 1 minus t sub c of z evaluated at that unstable pole location. We need that expression to evaluate to 0. Or that's really now saying that t sub c evaluated at 1.5 needs to equal 1. Well, we can do that actually because we have an unknown variable k in that expression, and we don't have to introduce anything additional into our desired closed-loop transfer function because restriction 4, steady state accuracy, is not addressed in the problem specification. So here we can say, oh, we have k, and now we replace z with 1.5. Our pole was at 0.79, and we need that to equal to 1. K now needs to be 1.5 minus 0.79, or 0.71. That's now this with k equal to 0.71, and in fact that's what that particular answer indicates. what is the transfer function associated with the following unit step response? Here, this is a little bit tricky because it's happening so quickly in terms of the peak. But usually it's beneficial to play with percent overshoot and peak time to determine where my closed loop pulls. And this is now for a unit step. We've injected a 1, so now whatever we're doing, eventually we need g sub c of z, and we're told that we can assume this is a second order and we have 1, 0 at the origin. We know that when we evaluate whatever we end up with at 1, we better end up with our DC gain equaling 0.25, because we put in a unit step and we get out a 0.25, so y final is equal to g sub c of z with z equal to 1 times our unit step 1. This is 0.25, so that's now what g sub c of z evaluated at z equal 1 needs to be. Our percent overshoot in this example is, we max out at 0.35, we eventually settle at 0.25, and now we multiply that by 100%. That now gives us a 0.1 over 0.25, or a 10 over 25, or that's now 2 5s over 5 5s, or that's now 40%. I kind of didn't include this, but you can include that throughout and see that now our percent overshoot is 40%. Now we could go here and we could say, oh, we have a 40% overshoot. Now I know that my damping ratio is 0.28, roughly. If I now have a damping ratio of 0.28, what does that allow me to do? Well, now I have that, and I can look at my time to peak. Time to peak is pi over omega sub d in the analog setting, and we know that theta sub d in a discrete time setting is omega sub dt. Now we can use that information to actually determine or solve for theta sub d based on when we peak. And here it peaks really fast. Here is one sample period, so that's what this is, capital T. Here is our second, so we're peaking, and now you need to be a little bit more liberal with when you peak, because that peak is occurring sometime between 2t and 3t samples. Because if it occurs at 2t, then we would go into our z-plane and see, oh, that corresponds to 90 degrees. Well, maybe we need to connect that with this particular zeta value and use these two extreme, or these two limiting values of our peak time to say, oh, our peak time actually probably occurs somewhere between 2t and 3t. Let's see what that actually means. So here we have a time to peak and a theta sub d expression. Let's now solve this for omega sub d. Or we could solve it for time to peak, whichever way we want to do it. So time to peak is now pi over theta sub d over t, so this is pi t over theta sub d. That's our relationship now between time to peak and theta sub d. If we have 2t for our time to peak, we can cancel the t's and we can see that theta sub d is now pi over 2, or that's 90 degrees. In degrees, in radian measures, it's pi over 2. If we actually had a 3t time to peak, now our theta sub d, canceling the t's, is now going to be pi over 3, or 60 degrees. Which, what I'm saying really is that, and which one do I want to use? Maybe I go all the way back here, and say you need to maybe have available to you something like this. Now we said that we are somewhere by 0.3. We're at 0.28 for our zeta value, and we're between 60 degrees and 90 degrees. So we should be looking at poles somewhere in that sort of yellow highlighted region. Is that true? Here's 10, 20, 30, 40, 50, 60. So we are now between, we would expect our dominant poles to be somewhere in that shaded region. And that now might help us then when we look at this problem and try to find what transfer function actually corresponds to those values. And if you now factor this one, you'll see that it's z minus 0.2 squared plus 0.6 squared. So that means that this one would have poles at 0.2 plus and minus j 0.6. And if we go back to what I just had, now that said that we were at 0.2 plus and minus 0.6. And that's actually, if I could draw a straight line, that's probably the correct answer. If you start doing it other ways, you might find that, wait, I don't see any of these, but you can also double check that this in fact does have the DC gain that's necessary, and so that is in fact the transfer function for this particular system identification problem. Assuming a standard control loop configuration with a controller in a plant using a non-negative gain K interconnected with negative unity output, that's our standard structure. If C of Z is K and G of Z is this transfer function, select the correct answer. So now I would just recommend that you immediately just start sketching the root locus associated with this particular system. We have a pole at 1, and we have another pole at 1.5. We have a 0 at minus 1/2, and we have another 0 at 1/2. Now, what's the root locus? Well, we know this segment belongs to the root locus. We know that segment belongs to the root locus. And that's all the segments of the root locus that belong, or I'm sorry, that's all the segments on the real axis that belong to the root locus. We have 2 branches there and 2 branches here. These 2 break away and re-enter. It may not be a true circle, but they're going to come over there, and that means then that we will have the opportunity to have both branches. Once both branches get to that location of gain, we can crank up the gain beyond that, and all of this and all of this stay in the unit circle as we crank up the gain from some, let's say, lower limit, K delta, up to, and we can crank up the gain all the way to infinity. Even though this is a finite distance in the z-plane, we actually can stabilize this system with an infinite range of gain K, because now our K for stability lives between some lower limit and it goes all the way up to infinity. So now, as long as K and this is bigger than 0. So K is an infinite, has an infinite range, and that's why answer 2 is correct for this particular problem. Again, assume the standard control loop configuration with a controller in a plant that is interconnected with a C, a constant gain controller, and a plant G. What is the maximum value of gain K to achieve stability? Here, I would just start sketching the root locus. We have a pole at the origin. We have another pole at 1/2, and we have a 0 at -1/2. Well, this is our story. This is 2 poles to the right of a 0. We can determine what that breakaway point is going to be, or what our circle radius is going to be, by the geometric mean. The geometric mean now is the square root of 1/2 and 1, or it's the square root of 1/2, which is the square root of 2 over 2, or it's 0.707. So that now, right here, is 0.2 beyond the origin. Here we have our -1. Again, this was -1/2, so we will actually re-enter at 1.2. So this now is our circle. One pole goes there and one pole goes there, and what we're interested in is what's happening with respect to our unit circle. Well, for low values of gain k, we're stable. This one now comes up here. This one comes down there, and whoa, we actually go unstable when we crank up the gain to go beyond that point. What we need to do then, for the maximum gain k to achieve stability, we need to now find what is k box. But we can find box. We could do it many different ways. Maybe the most straightforward, since we just have 2 poles, would be to just say, wait a minute, we know that's now a unity, so we know that if this is, let's say, what have I been calling it? Let me just call it x plus jy. We know that x squared plus y squared is equal to 1. We also know that this distance, that was our radius r, and r was 0.707. So we can now find that either using, now we could use the law of cosines if we wanted to. We don't have any right angles, that's why we're using the law of cosines to find that. Or you could find another way, might be to say, wait a minute, I know my closed loop transfer function or system is now 1 plus k times whatever I had. What was it? Z plus 0.5 over z times z minus 0.5. That's going to determine my closed loop poles. If I now look at the numerator of that, I now have z times z minus 0.5 plus k z plus 0.5 equal to 0. I can multiply that out. I have z squared minus 0.5z plus kz plus 0.5k is equal to 0. Now I know that when I reach this box, my roots of my characteristic equation have to have magnitude of 1. Well, if that's the case, I now know that the constant term in this expression is equal to 1. That now says that I have 1/2 k is equal to 1 at the box, and that's going to determine my maximum value of gain. So my k at box, which is k max, is 2. And hopefully that's what I have for the answer. Now some people may have said, oh, I know that the maximum gain value is always at -1. No, that's not always the case, because here, once you exit the unit circle with one of those poles remains outside the unit circle. Let's just say it's this one. The other one does come around and come back in, but this value of k at -1 might evaluate to one of these given answers, but it's not the maximum value of gain for stability. We've already surpassed that once we hit the box. We can't say, oh, I know, it's always going to be that value of k when z is equal to -1. No, 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 that's not always the case. Assume a standard control loop configuration and a non-negative gain. Determine the range of K for stability when we have a constant gain controller and we now have this G of Z. I would sketch the root locus. We have a 1.5 for a pole. We have another pole at minus 0.5. Well, this is a pretty easy root locus diagram. We now have these two coming together and they meet halfway between. We only have two poles, no other poles or zeros in here. These are 2 units apart, so they are going to meet 1 unit away from each other, or from the original starting location, which says that now at 1/2, one is going to go up and one is going to go down. We are wanting to know what's the range of K for stability. Well, the very first thing we can see is, I hope, that we're not stable initially, so we need to crank up the gain K enough to get us to that location. This pole over here is always stable until we what? Till he exits that particular point, and this one, this branch, he doesn't become stable until he reaches 1, so that's going to be our lower limit, and the upper limit is going to be the triangle. So K now is going to be bounded between box, in this case, and triangle, the way I've defined it. And K is, in this case, Kg is equal to 1. We solve that for K, and K is now, there's no constant other than unity there, so we don't need to divide by anything. This is now Z plus 1/2 and Z minus 1.5. K box is going to be that expression for K evaluated at Z equal to 1. So this is now 1 plus 1/2 times 1 minus 1.5, and we're taking absolute values. So this is now 1.5 times 1/2, or this is now 0.75. That's our lower limit on the stability. We now need to find what is happening relative to the triangle, and we know where that is. We now know that Z triangle is in fact having a real part of 1/2, and why? We can know what, or we can solve for that because we know the magnitude of Z delta is equal to 1. So now we know that y is going to equal the square root of 1 minus 1/2 squared, or this is now, I hope I'm doing the algebra right, square root of 3 over 2. You won't be able to tell because my notation is so sloppy, but this is now 1/2 squared. This is now 1/2 plus j square root of 3 over 2, and we can now plug that value in to find what, did I label it as a triangle? Now K triangle is 1/2 plus j square root of 3 over 2 plus 1/2 times 1/2 plus j square root of 3 over 2 minus 1.5. Or this is now 1 plus j square root of 3 over 2, and this is minus 1 plus j square root of 3 over 2. Those magnitudes are the same. It's just the negative of the real value. So we now have 1 squared plus square root of 3 over 2 squared, square rooted times that same thing square rooted. So let's not even worry about that product. It's just the real part squared plus the imaginary part squared. 1 plus, this now becomes 3/4, so our upper limit is 1.75, and hopefully that's now what we had. Find a gain value K that will locate closed loop poles at 0.25 plus or minus j 0.25 when the plant is controlled using this controller C of Z. Again, start with, and don't get too lost by the factoring, which is what I have a tendency to do. We have poles in our plant at 1/4 and 3/4. We actually have, this is a PID controller, we have a pole at the origin and a pole at 1, and in fact we're canceling those stable poles with our zeros of our PID controller. So now you can virtually eliminate those X's and O's that are canceling each other. They're effectively not there. Our root locus now is going to be the standard root locus diagram. This has a real part of 1/2. Wait a minute. We were being asked for a real part of 0.25. That's not even going to happen for this, so there's no K that will allow this controlled system to have closed loop poles at 0.25 plus and minus j 0.25. So you can't just blindly substitute 1/4 plus and minus j 1/4 into your K formula. The answer here is none of those numerical values, because there's no K that will be allowing you to produce closed loop poles at the triangles, because those triangles don't even live on the root locus. Another PID controller. Now let the zeros be located at the same location. Now just remember, you now have 2 zeros at alpha. We have a pole in our plant at 1/2. We have a PID controller, and we're wanting our Z delta to be at 1/2 plus and minus j 3/4. Well, if we could start looking at these and say, oh, what if I put both zeros at 1/2? Well, if you did that, you would cancel one of those, and then you would have an extra 0 there. So effectively, you would now have, can I sort of do this? Let's see if we're okay with this. Now you effectively have a 0 there, and what's the root locus? Well, now the root locus is there and here, and there's no way that you get up to that triangle. So that's not going to work. This one is no good. What about 0.25? Well, what happens if we have both zeros there? That might work. And what you need to do then is start figuring out, okay, I now need to find the values for theta sub z that cause the root locus to go through that triangle, and that's going to happen if that triangle, the phase at that triangle, has an angle of minus 180. I don't know what I want to call this. Let me call this theta p sub 2, and this is now theta p sub 0. So that now if I had that, I would say, oh, I have 2 angles at the same location, so I have 2 theta z's, and now I'm subtracting my theta at the origin due to the pole at the origin. I have another pole at 1/2, that I called theta p sub 2, and I have theta p1 for the pole at z equal to 1, and those have to be minus 180. I know all of these angles, or I can calculate those. Theta p0 is now the angle that has a tangent. I go up 3/4 and over 1/2. This ends up being about 56.3 degrees. But look what theta p1 is. Theta p1 is in fact 180 degrees minus that same value. I went up for the acute angle 0.75 and over 1/2, and theta p sub 2 is 90 degrees. Now I can compute my theta z. I know I have two of those, I subtract 56.3 and 90 degrees and 180 degrees minus 56.3 degrees, and that needs to equal minus 180 degrees. This 56 cancels that, or is canceled by that minus 150. This minus sign together with that cancels that, and I now have 2 theta sub z minus 90 degrees is equal to 0, or theta sub z is now 90 over 2, or 45 degrees. That now tells me where my zeros need to be. They need to be in some location such that this angle, theta sub z, is 45 degrees. And that's going to be, I go up set 0.75, I need to go horizontally 0.75. I know those triangles are at 0.5, so I now need to be, in terms of a picture, here's my triangle. I know that triangle is centered over 0.5. Here's the origin, and it has a vertical distance of 0.75. I now need to be over here, 0.75, so my zeros are at minus 0.25. That gives me now this theta sub z of 45 degrees that I was after. Let's look at a few more that students have asked about. Suppose you're now trying to stabilize this unstable non-minimum phase system. We have a pole outside the unit circle, and we have a zero outside the unit circle. And if you're stabilizing a non-minimum phase or a unstable plant, you may want to not worry about trying to start with a PI controller. That's probably not going to happen. In this particular case, it's probably better to stay away from a PI controller initially. And probably the first attempt I wouldn't be using it. We have a pole at 2. We have a 0 at 1.5. We can't stabilize this system with a constant gain controller because that is stuck. If we look at a root locus of that, we're stuck there. So what do? Wait a minute. We could maybe try our story. If we did 2 poles to the right of a 0, now we know we have a circle. Oh, but look what happens. That radius of that circle is exactly 1/2, so I'll never get both branches of my root locus simultaneously inside the unit circle. So that pole won't work, but I'm kind of I'm on the right path. I hope you can see that. So now if I in fact, and you could just pick something a little bit beyond 2, you know that's going to put you inside the unit circle. The further into the unit circle, the more you want to put this over here. If we just put it at 2.5, that's going to give us our radius that we're comfortable with, or we've been playing with. Our radius, which is the geometric mean, is now the square root of the distances of those poles to that 0. We have one of those being 1/2. That's the pole at 2, and we have the other one. This was at 1.5, so this is now 1 away. This radius is now the square root of 1/2, or this is our familiar radius of 0.707. Now we're in business. Now these two meet. They break away at 2.2. This one now comes in, and it will be at 0.8. And then one will zip out there, the other will zip out there, but we do have a range of K that will allow us to stabilize the system, because now if we crank up the gain to get us to that triangle and not crank up the gain so much that we zip one of those out beyond the unit circle, so now one branch, let's say this guy comes up here, goes there, and then goes there. He's going to be in trouble if he cranks up the gain to get him to the box. This one is here, then there, and he's okay until he gets to the -1, and probably the box is going to occur before the -1. But you can see how many different problems I could start asking. But now, what k would we use? Well, I would probably use a k that's close to the breakaway. You don't want to be sort of teasing with that triangle. That's going to be kind of a challenge to find. You can find it. You know the law of cosines. You can find the box, but you don't want to be that big. But you can find the cloud. That's just the gain expression evaluated at, let's say, 0.8 to be really quick. So now we can say, oh, what's the gain at k equals 0.8? Was that one of our questions? Well, who knows? We just wanted to find a stabilizing, not z, we want to find a stabilizing c of z. And in this case, our c of z so far is just k over z minus 2.5. And that will bring us to our next story, which is, wait a minute, is that an acceptable controller? And in fact it is. But k at 0.8, we would find, what did we start with? We had a pole at 2. We had another pole that we introduced in our controller at 2.5. We had a 0 at 1.5, and our gain of our system was 2. So we now need to take that into account, and we can now evaluate that at 0.8 so that our stabilizing controller, we now found the pole. It was at 2.5. We do this computation, and hopefully I've done that properly. It's now 1.457. We could find what's the upper limit on k, or what's the minimum k. So k minimum is k triangle. I tried to compute that earlier using the law of cosines, and that ends up being, if I'm doing my math right, about 1.33. K max is either k at -1 or k at 1. It in fact turns out to be at k1. You do that and you end up with 1.5. So any k between 1.5 and let's say 1. Let's go a little bit bigger than that, 3, 4, that would be stable. And our controller, let's say we now just say, okay, let's just go to 1.4 over z minus 2.5. That would now be a controller that stabilizes that closed loop system. And here's our stability range on our k in this single pole controller. We didn't even need a 0, but what did we do? Here's that story where we have two bads make a good. We had an unstable plant, we introduced an unstable controller, and we cranked up the gain to this Goldilocks value of 1.4, whatever I did, and voila, we have a closed loop system that is stable. Well, that kind of brings us to this issue. Our controller in that particular case was k over z minus 2.5. Is that controller okay? It's unstable, but it gave us a stable closed loop system. Well, in fact, because we have a pole zero excess of 0 or more, this does correspond to a causal controller. Let's look at that concept. For a causal controller, we need this transfer function between the input to our plant and our air signal. That's what's defining C of Z. That transfer function needs to be proper or strictly proper. Proper means that the numerator order is the same or equal to the denominator order in this transfer function. Strictly proper means that the degree of the denominator exceeds the degree of the numerator. Or you can say that we actually have a pole. No, I'm sorry. We have a zero at infinity. We have a pole zero excess of 1, so we have a 0 at infinity. So if we have zeros at infinity, we have a causal controller. Suppose we wanted to look at that. Suppose now you have this transfer function c of z equaling k over z plus 1/2. So now we know that u of z over e of z is k over z plus 1/2. We can now convert that into a difference equation that possesses delays by multiplying by 1. We now have kz to the minus 1. This is now 1 plus 1/2 z to the minus 1. Cross multiply. Take it into the time domain, and we now see that we have u of n plus 1/2 u of n minus 1 equaling k e of n minus 1. So that in fact this is the present input u is a function of previous inputs or current inputs and previous air signals or present air signals. In this case, it's both previous input and previous air. If you had a proper transfer function, you could have present air signals, but that's okay. That's still considered a causal controller. So, causal controller is okay, and it's valid to have a controller that has more poles than zeros, because we've been dealing with that too. We've also dealt, what's the simplest proper controller? That would just be a pure gain. Now we have the same numerator order as denominator order, and the present input to the plant depends on the present air signal. That's what happens with a proper controller, and the most simple proper controller. Let's do one more. Let's look at the departure angle from a pole at 1 plus j1 in this transfer function. That was a question that someone asked. Let's see if we can believe the answer. Now we're trying to find the departure angle in a root locus diagram. We have 4 poles, there's no zeros, and we want to know what's the angle at this dot, and that dot is infinitely close to that pole at 1 plus j1. Remember, maybe what was causing the issue was the fact that we have 2 poles at the origin. So we're going to have 2 angles. We'll have 2 theta sub p sub zeros. We'll have an angle theta p bottom, I'm calling it, and we have the angle due to the pole that's departing, or the root locus branch is departing from that upper pole. The phase angle condition then, I'm looking to see if I've done anything below that. The phase angle condition now says that we have no zeros minus the angles of our poles, the departure angle plus theta p0 plus theta p0. We had 2 of those. I'm trying to be explicit. Plus that pole at the bottom, those have to equal minus 180 degrees. Well, that pole up in the first quadrant is at 1 plus j1. I hope you can see then that the theta p sub 0, we go up 1 and over 1, that's 45 degrees. And we have 2 of those, so we have 45 degrees here. We have 45 degrees here. theta p bottom, we have to look up 90 degrees there. We have 180 degrees total there, and we'll have that with a negative sign. We now have minus alpha d minus 180 is equal to minus 180. These two cancel, and now we have alpha sub d, or negative alpha sub d, equaling 0. So our departure angle is 0. All that says is that we're leaving, we're exiting. And what does the root locus of this look like? Well, we know infinitesimally close to that pole we're going to the right, and we're going to match that. We're going to mirror image that down there. What happens to these? Do we have any real axis segment belonging to the root locus? There's no odd poles or zeros to the right of anything. These poles have to exit immediately. These are going to exit. We can think about rule 4 and say, well, what are our asymptotes? Well, our asymptotes now are determined by the pole zero excess, which is 4. So we have a fundamental asymptote angle of 45 degrees. We have another one at 135 degrees, etc. So this one is going to go zipping off to 45 degrees. This one is going to be going off to minus 45 degrees. This will be going off to 135, and that's now the rough sketch of what this looks like root locus wise. We weren't asked that. We were just asked for theta sub d, but I hope you see that we can have a 0 degrees for a departure angle from our complex poles. I hope that's now enough to get you ready and excited to finish up this class via the final exam. Good luck.